Picture this. You're on vacation and you see a mesmerizing landscape. Wanting to take a picture to remember this beautiful scene, you pull up your phone, you open your camera, and suddenly you receive a warning. Uh-oh, storage is full. Does this look familiar to anyone? I know it does for me. But this is a bigger problem than you might think. Our storage capacity can no longer meet our demands. 2.5 quintillion bytes of data in the form of videos, pictures, and documents are generated every single day. And the gap between the data generated and our capacity to store it will widen unless we seek alternative storage media. So, what is DNA digital data storage? It's a process of encoding and decoding binary data to and from synthesized strands of DNA. Well, what's binary data? In the computer you're using right now to watch this video, or to be on this call, photos, documents, and audio tapes, as well as videos, are represented as binary digits or bits, which can be either 0 or 1. And how does DNA fit into all of this? Well, deoxyribonucleic acid, or DNA, contains the genetic instructions of all living organisms. And so DNA is the earliest DNA of the earliest humans and woolly mammoths has lasted thousands of years, allowing us to read even today their genetic information. We were able to uncover how the earliest organisms lived, what they ate, and how they died. So DNA is proven to be incredibly powerful, durable, compact, and stable. But why stop at genetic information? Couldn't DNA store other kinds of data? To preserve the digital data we're producing in massive quantities, we could repurpose the storage capacity of DNA. And so the sequence can be considered a string of 4 biological compounds, or bases: adenine, guanine, cytosine, and thymine. And the order of these 4 bases forms the genome of an organism, but can also be manipulated to code for digital data instead. And how is this done? Well, there are 6 steps. Firstly, you would have to code. From the binary sequence of digital data, we can assign a single letter base to a 2-bit binary code. The mapping of characters to bases is very straightforward. 00 becomes A, 01 becomes G, 10 becomes C, and 11 becomes T. So if I took the word DNA, I would convert this to a binary sequence, and then from there have it be represented with single letters A, C's, G's, and T's. And so I decided to build a program that could automate this instead. And for the sake of this presentation, I decided to put the article I wrote about this in my program. And so I was able to have a really long sequence of DNA, which was then representing my article. And so from there, it would be possible to hop onto the next step, which would be synthesis. And from there, synthetic DNA molecules that store the information are artificially made in a lab, and they don't come from humans or other living organisms. And companies like Twist Bioscience translate the sequence of bases into DNA molecules, which can then be stored in tubes. But to preserve DNA, it would have to be in certain conditions where it can be frozen and in a vacuum-packed containers. So exposure to heat, water, and sunlight can cause the molecule to degrade faster. 4th step would be to retrieve it. And to retrieve the DNA sequence, or the DNA molecules, PCR, which is a popular lab protocol, is used to copy the DNA and then zoom in on a targeted section. This way, only the sequence that codes for digital information can be read, not the entire thing. And 5th step would be to sequence it when we determine the order of the 4 bases that make up the DNA molecules. And from those 4 bases, we can decode. And so we reverse the 1st step and convert every base to a 2-bit code. From the binary sequence, it becomes possible to convert your data to the digital format. And there you go. And now my question to you is, what do cat photos, the Universal Declaration of Human Rights, the music from Super Mario Brothers, and great literary works have in common? Well, all of these files were stored on DNA strands and retrieved without errors. This technology works, and some of the pioneers in this field are Microsoft and Twist Biosciences. And so we used to store data on rocks, hard drives, and floppy disks, but they've now become obsolete. And we can't retrieve encoded information from such storage media. But with DNA, digital data storage, we don't have to worry about losing information, because as long as there's life on Earth, we'll be interested in reading, preserving, and writing DNA. And so to put things into perspective, Think of compressing all of the information on the accessible internet into a shoebox. With DNA data storage, that's possible. And so at the moment, with the DNA sequence of some of the pictures or articles I wrote, I would like to synthesize this. And so I'm communicating with a couple of Twist Bioscience employees, hopefully to send my genetic code to them and have them synthesize a couple of DNA molecules that I could then keep and have with certain pictures of family members. So this is technology that exists and that we can use instead. For the technology, though, to scale, we would only have to commercialize it. And for that, there would have to be lower costs and better technologies that can read and write DNA. But this is all in development, and I'm very optimistic that this is coming soon. So my question, final one is, well, what would you store in DNA?